This is the beginning of Unit 5. Unit 5 is some more applications of derivatives that we're going to see, and in this video we're going to focus on learning target 5a, which is called LHopitals Rule. So LHopitals Rule allows us to actually shortcut some of the derivatives that we took back in Unit 1, but only certain derivatives work with LHopitals Rule. So this is another way to take limits when we have this indeterminate form of 0 over 0 or infinity over infinity. If we don't have that indeterminate form, then LHopitals Rule will not work. So to read our LHopitals Rule, which is a theorem, it says that suppose that f of a, which would equal g of a, is equal to 0, or that f of a, which would equal g of a, is equal to infinity. So meaning when I do a direct sub in, a is the value that x is approaching in the limit. If I directly sub in and I get 0 for the function on top and 0 for the function on bottom, or if I directly sub in our a value for x and I get infinity for our value on top and infinity for our value on the bottom, and if f and g are differentiable on the open intervals, since this will involve us taking a derivative, I have to make sure my derivatives exist, and assuming the derivative of our function g is non-zero, then our original limit as x approaches a of f of x over g of x, so this original limit would be equal to the limit as x approaches a of f prime of x over g prime of x, assuming that limit exists. So what this means is that if we were to sub in the value that x is approaching, so as x approaches a, if we were to sub in that value into the top function and the bottom function, and we get both 0 and over 0 or infinity over infinity, then instead of doing some of the algebraic manipulation that we learned back in Unit 1, like factoring or conjugates, common denominators, or powers of infinity, then we can just take the derivative of the top and the derivative of the bottom separately and evaluate that new limit. So what LHopitals Rule tells us is if I were to do a direct sub in and I get the indeterminate form of 0 over 0 or infinity over infinity, then instead of looking at my original limit, this is equivalent to looking at the limit of the derivative of the top over the derivative of the denominator. I do want to warn you that this is not the quotient rule, so I am not applying the quotient rule here at all. I am separately taking the derivative of the top function and separately taking the derivative of the bottom. And something really important to note is that in order to use LHopitals Rule, just like when we use the intermediate value theorem, we have to explain and state how the conditions are met. So for LHopitals Rule, the condition that needs to be met is that when we do a direct sub in, we get 0 over 0 or infinity over infinity. So to use LHopitals Rule on an AP free response, or to use it on any learning check or final in my class, you must show that the limit of the numerator goes to 0 or infinity, and that the limit of the denominator also goes to 0 or infinity separately. So you have to first compute those two separate limits and state that we are using LHopitals Rule. So let's look at our first example. We're asked to evaluate this limit. We have the limit as x approaches 0 of the square root of 1 plus x minus 1 all over x. Now, if I were to do a direct sub in, I can see that I get 0 over 0. So we could do some algebraic manipulation. We could multiply it by the conjugate, and that would help fix that issue. But instead, let's use LHopitals Rule. Before I can apply LHopitals Rule, I have to show that the conditions are met. So I need to separately show that the limit as x approaches 0 of our numerator, I need to show what that limit goes to, and I also need to show that the limit as x approaches 0 of the denominator and what that limit goes to. Now if I do a direct sub in for the square root of 1 plus x minus 1, I'd end up getting 0, since I'll get the square root of 1 minus 1. And if I do a direct sub in on x, I just get 0 then. So the conditions for LHopitals Rule are met. So what this tells us is that by LHopitals Rule, so I do need to write out what I'm using. Oops, forgot that's there. By LHopitals Rule, our original limit as x approaches 0 of the square root of 1 plus x minus, made that square root too long, just that, minus 1 outside the square root all over x, that is going to be equal to the limit as x approaches 0. And now I get to take the derivative of the top and the derivative of the bottom separately. But before I can get to this step, I do have to show that both the limit of the numerator goes to 0 and separately show that the limit of the denominator goes to 0 as well, and state that I am using L'Hopital's rule. Now that I have met the conditions of L'Hopital's rule, I can take derivatives. So to take the derivative of the numerator, that will be a chain rule. I have that 1/2 as the square root comes down, keep the inside the same. So I get 1 plus x to now the negative 1/2. Derivative of negative 1 drops to 0, and then the derivative of x is equal to 1. So since the limit of the numerator was equal to 0, the limit of the denominator was also equal to 0, then by L'Hopital's rule, instead of looking at this original limit, it is equivalent to looking at the limit of the derivative of the numerator over the derivative of the denominator. Now from here, this limit is actually a direct substitution that I can sub in, and I'll get 1/2 times 1 to the negative 1/2, which technically I'm allowed to leave on a free response since my answer is completely numeric. But if you were unsure if this was truly going to work as a direct sub, that 1 to the negative 1/2 would be the same thing as 1 over the square root of 1, which we know is equal to 1. So 1/2 times 1 would give us 1/2. And any of these answers would work as our final answer since all of them are numeric. So here's our first example of using L'Hopital's rule. And we can see this, it works since I get that 0 over 0 indeterminate form. I never want to write equals 0 over 0 because that limit is not equal to 0 over 0. That's an indeterminate form. Instead, we show that by computing the limit of the numerator going to 0 and the limit of the denominator separately going to 0 as well. Let's look at example 2. So example 2 here says we have the limit as x approaches infinity of 6x to the 4th plus 1 all over 9x plus 2. So this is one of those infinity over infinity cases. If I separately compute the limit as x approaches infinity of just the numerator, I can see that that limit is going to go to infinity since I'd have a really big number to the 4th power, which is still a really big number, times 6 makes it even bigger, plus 1 makes it even bigger from there. So my limit of the numerator is going to infinity, and I'll also show that the limit as x approaches infinity of the denominator, so I'm computing these limits separately, that is also going to be equal to infinity as well. So by L'Hopital's rule, we can, instead of computing the original limit, which was the limit as x approaches infinity of 6x to the 4th plus 1 over 9x plus 2, that is going to be equal to the limit as x approaches infinity of now I get to take the derivative of the top over the derivative of the bottom. So I show that the conditions are met by computing both the limit of the numerator and the limit of the denominator. And since I get infinity for both, I have that indeterminate form of infinity over infinity. So by L'Hopital's rule, my original limit that I have is going to be equal to the derivative of the numerator. So the derivative of 6x to the 4th plus 1 will give us 24x to the 3rd. And the derivative of 9x plus 2 will just give us 9. So that original limit is now equal to my new limit. This can be a direct substitution in. If I were to directly sub in infinity for x, then I'm going to get positive infinity out, since I have a positive number to the 3rd power, which is still positive, times 24 divided by 9 still keeps that at positive infinity. So this is how we would apply L'Hopital's rule for one of our limits as x approaches infinity. But I do want to point out that there's actually a faster way to do this limit that we had back in Unit 1. So although there are times when L'Hopital's rule can be applied, to help you save time, unless the problem says using L'Hopital's rule, you don't have to use L'Hopital's rule. You can still use all the algebraic manipulations that we had before. So for example, in example 1, we could have multiplied by the conjugate and simplified. In example 2, we talked about the powers here, since these are limits to infinity, and the fact that the degree in the numerator is higher, then my limit is either going to go to positive infinity or negative infinity, and it would end up going to positive infinity since the ratio of my leading coefficients here is producing a positive number. So it is still fair to say that the degree of the top here is larger than the degree of the bottom, and compute your limit that way. So we will see some examples that you might prefer to actually use our old methods with, because those are actually faster to solve some of these, Or if you want to use L'Hopital's rule with them, then we can see as long as we state that the limit of the numerator was equal to infinity, the limit of the denominator was equal to infinity before applying L'Hopital's rule, then we can still apply L'Hopital's rule for those problems as well. Let's look at some more examples. So in example 4 here, we have the limit as x approaches 4 of x squared minus 4x over x squared minus 3x minus 4. Why don't you guys pause the video right now and determine if you could use L'Hopital's rule. So to determine if I can use L'Hopital's rule, I need to see what the limit of each part of this fraction is going to go to. So let's compute the limit as x approaches 4 of x squared minus 4x. So I'm doing the limit of the numerator. If I do a direct sub in, I'll get 16 minus 16, which would give me 0. And I can do the same kind of check for the limit as x approaches 4 of our denominator, which is x squared minus 3x minus 4. If I do a direct sub in here, I'm going to get 16 minus 12 minus 4, which would end up giving me 0 as well. So yes, I am able to apply L'Hopital's rule since a direct substitution leads to 0 over 0 for my original limit. So by L'Hopital's rule, this original limit that I have as x approaches 4 of x squared minus 4x all over x squared minus 3x minus 4 is going to now be equal to the limit as x approaches 4 of the derivative of the numerator, which would be 2x minus 4, over the derivative of the denominator, which will be 2x minus 3. So since the limit as x approaches 4 in the numerator was equal to 0, and the limit as x approaches 4 of the denominator is also equal to 0, then I can apply L'Hopital's rule, which tells me that my original limit is equal to the limit as x approaches 4 of the derivative of the numerator over the derivative of the denominator. This can now be directly substituted in, and I'd get 2 times 4 minus 4 over 2 times 4 minus 3, which I am allowed to leave my answer like that. It is a numeric answer, but if you'd like to simplify it down, we get 8 minus 4 on top, which would leave us with 4, over 8 minus 5, 8 minus 3, which would leave us with 5. And either of those would be our final answer. Let's look at example 4 here. So in example 4, we have the limit as x approaches infinity of the natural log of x over 2 times the square root of x. Why don't you guys pause the video right now and determine if L'Hopital's rule can be applied or not. So to check that, we've got to check to see what happens with the limit of the numerator and the limit of the denominator separately. So let's check each of those limits. So if I take the limit as x approaches infinity of the natural log of x, well, this limit would be equal to positive infinity. The way I think about it is if we think about what the graph of a natural log function looks like, this would be the graph of a natural log function over here on the right. And so slowly the natural log function is increasing over time, and eventually as x goes out to infinity, the y value will also go up to positive infinity. We can compute the limit of the denominator separately. So we have the limit as x approaches infinity of 2 times the square root of x. That limit is also going to be equal to infinity. So although I am taking a square root here, the square root of a really big number is still a really big number. If we look at the graph for that, it would look like this kind of half-wing graph that starts at 0, 0 and goes off from there. So the conditions of L'Hopital's rule are met, so I can use L'Hopital's rule then. So by L'Hopital's rule, what this tells me then is that my original limit as x approaches infinity of the natural log of x over 2 times the square root of x, that is now the same thing as taking the limit as x approaches infinity of the derivative over the derivative. So why don't you guys set up what those derivatives would be? The derivative of natural log is going to be 1 over x, and the derivative of 2 times the square root will be 2 times 1/2 times x to the negative 1/2 by using the power rule there. Now this looks really messy, so I'm going to clean this up before we try to take the limit, because right now I have this 1 over x, which could be producing some issues. The same thing down here. So let's just clean this up so it's a little bit easier to determine. So 2 times a half is going to cancel. Right now I have 1 over x in the numerator over, well, x to the negative 1/2 would be the same thing as 1 over x to the positive 1/2. And when I have a fraction divided by a fraction, I can multiply by the reciprocal of the denominator, and I'll get the limit as x approaches infinity. Let me erase these graphs that we had just so I have enough space. But we'll get 1 over x times the reciprocal of the denominator would leave us with x to the 1/2 over 1, which this is the same thing as the limit as x approaches infinity of x to the 1/2 over x. Because I have the same base, we can subtract the exponents, and I'd end up with x to the negative 1/2, since we do the top exponent minus that bottom exponent of 1. But that is the same thing as the limit as x approaches infinity of 1 over the square root of x. And that is a lot nicer to see than that original mess that we had when we took the derivative. From here, I can actually take this limit directly, and that limit is going to be equal to 0. Since I'd end up getting a really large number in the denominator, 1 over a really large number that's getting infinite over time is taking that whole fraction smaller and smaller down to 0. So here's one of those infinity over infinity cases of L'Hopital's rule, where we could not really compare the degrees. We could think about these two functions and think about, well, what's happening with the natural log graph over the square root of x graph, but those graphs actually kind of look really similar, so it's a little bit harder to determine which function is dominating here. So this is one of those cases where L'Hopital's rule can really solidify for us that 2 times the square root of x is ultimately dominating in this function, which is forcing this whole limit then to go to 0. But make sure, as always, you have to be showing that the limit of the numerator and the limit of the denominator first. Compute each of those. By computing these, it's saying that I do have this indeterminate form of infinity over infinity, and therefore I can apply L'Hopital's rule. And right here is where I'm applying L'Hopital's rule, since my original limit is going to be equal to the limit of the derivative of the top. So the derivative of natural log was 1 over x over the derivative of the denominator, which was that power rule to get us 2 times 1/2 x to the negative 1/2. Let's look at example 5. Why don't you guys pause the video and do example 5 on your own first, and then we'll check it together. So let's check example 5. I want to see if L'Hopital's rule will work. So I can have to take the limit as x approaches negative 3 of x plus 3. That's going to give me 0. And I'll do the limit as x approaches negative 3 of the denominator, which will leave me with x squared minus 9. If I directly sub in here, negative 3 squared is going to give me positive 9. 9 minus 9 will give me 0. So yes, I can use L'Hopital's rule then. Oops, L'Hopital, there we go. And what L'Hopital's rule tells me is that instead of looking at my original limit, which was the x plus 3 over the x squared minus 9, since the limit of the numerator was equal to 0 and the limit of the denominator is equal to 0, we have this indeterminate form of 0 over 0. So my original limit here by L'Hopital's rule is going to be equal to the limit as x approaches negative 3 of the derivative of the top, which would be 1, over the derivative of the denominator, which would leave us with 2x. This limit can be directly substituted in, and I'll get 1 over 2 times negative 3, which I can leave as my final answer, or I could simplify this as negative 1/6 by multiplying the 2 and the negative 3. Another way to do example 5, if we were back in unit 1, we would have factored and canceled our like factors that we had, but sometimes L'Hopital's rule might be a quicker way to get you there. But if you notice the factoring right away, it might be quicker for you to actually factor and cancel than having to worry about showing the step of the limit of the numerator going to 0 and the limit of the denominator going to 0 as well. So it is still up to you guys if you guys still want to use all of those old rules that we had. If we can factor and cancel or use a conjugate, feel free to still be using those rules. I just want to show you guys how we can now have an application of derivatives and apply this. And the reason we didn't talk about L'Hopital's rule back in unit 1 was we didn't know how to take the derivative of every single function. Now we have all of our derivative rules, and we know how to take the derivatives of not only polynomials but also log functions. Maybe if we have some trig values in here, all of those derivatives we can now take, so it makes sense for us to now start talking about L'Hopital's rule. Back in Unit 1, we didn't have all the rules for derivatives, so this would not have worked out. Let's look at example 6. Why don't you guys pause the video and try example 6 on your own, and then we'll check it together. Okay, so to check example 6, if I were to separately compute the limits here, I would get infinity over infinity. But what I notice is that this is one of those powers of infinity problems, and I can tell that the degree of the top here is going to be larger than the degree of the bottom, which would mean that my two options are either positive or negative infinity. Now my leading coefficients here is that negative 5x, or my leading terms, negative 5x cubed over 2x squared, and that would leave me with a negative 5 over 2x when I reduce it down, and so this limit will be equal to negative infinity using our limits to infinity rules that we had from before. Well, let's think about how we would do this with L'Hopital's rule. So I would have to separately show that the limit as x approaches infinity of the numerator, that limit would actually be going to negative infinity, and that could still work out. And the limit as x approaches infinity of our denominator is going to 1 plus 2 times x squared. That's going to positive infinity. Now this is fine. Yes, I do have negative infinity over infinity, but I just have a negative 1 times the infinity over infinity if we were to take out that scalar. So L'Hopital's rule will still hold, so I can still use L'Hopital's rule. L'Hopital's, I'm writing ahead of myself. So our original limit as x approaches infinity of negative 5x cubed plus 1 all over 1 plus 2x squared, that's going to be equal to now, using L'Hopital's rule, the limit as x approaches infinity of negative 15x squared by using the power rule all over 4x. Now this limit as it stands right now, I can't actually sub in directly because I'd get another case of this infinity over infinity. But what I notice is that I can reduce this down. Since there's no more coefficients or not coefficients, but no more constant terms that are added here, I can reduce this limit down to be the limit as x approaches infinity of negative 15x all over 4 by reducing the x squared over x. And now from here, if I were to directly sub in, I'll write my final answer up here, but this would be equal to negative infinity. So L'Hopital's rule does work as well, but as we compare kind of the work on the side here, it's a lot quicker to just theoretically think about what's happening with your function, and there's no work that really needs to be shown with this first route. If you're going to use L'Hopital's rule, then you have to show the work of separately computing each of those limits and showing that they go to infinity, and then having your original limit equal to your new limit, reducing it down from there. So in my opinion, I think L'Hopital's rule takes way more work in a scenario like this. It still will work, but as we think about, we want to be wise with our time and we want to make sure that we're using our time appropriately, some of our old methods are actually better that we had compared to using L'Hopital's rule on some of these problems. Let's see, we have two more examples. So example 7 says the limit as h approaches 0 of 2 plus h to the third power minus 8 all over h. So let's see if L'Hopital's rule will work. So I'll separately compute the limit as h approaches 0 of 2 plus h to the third minus 8. If I do a direct sub in here, I get 2 cubed, which is 8. 8 minus 8 will leave me with 0. And I'll do the limit of the denominator. So the limit as h approaches 0 of just h is equal to 0 as well. So L'Hopital's rule will work. So why don't you guys write out what our new limit would be equal to using L'Hopital's rule, and then compute that limit, and we'll check it together. So using L'Hopital's rule, I know that my original limit, which was this 2 plus h cubed minus 8 all over h, is equal to the limit as h approaches 0 of using the chain rule here. I'll get 3 times 2 plus h squared times the derivative of the inside there is 1. The derivative of negative 8 drops to 0, all over the derivative of h is equal to 1. So here we don't have x's, but our h is our variable, so that's what we're taking the derivative with respect to. Now I can actually directly substitute in here, and I get 3 times 2 plus 0, so 2 squared. If we want to simplify that down, it'd be 3 times 4, which would give us 12. And either of those would work as your final answer on a free response. And for our last example, we have the limit as x approaches 0 of 8x cubed minus 5 over 4 minus 3x to the 4th. Why don't you guys pause the video and do example 8 on your own first, and then we'll check it together. So to check example 8, we could use L'Hopital's rule, and I'll write that out in a second, but I notice that I think it's a little bit easier to determine the powers here. And what I see is that the degree of the bottom is actually the larger of the two, since I have an x to the 4th versus an x cubed. So that degree of the denominator is larger than the degree of the top, so I know that right away that limit is going to be equal to 0, since the degree of the denominator is larger than the degree of the numerator. Now, if we worked it out with L'Hopital's rule, we'd have to first show why we can use L'Hopital's rule. So we're separately computing these limits of limit as x approaches infinity of the numerator, which would equal infinity, over the limit as x approaches infinity of our denominator here. That would leave us with subbing in a positive number to the 4th, which is positive, minus 3 though, so I would end up with negative infinity. That's fine, L'Hopital's rule still applies. It's an infinity over infinity case. So by L'Hopital's rule, let me see where I have enough space here. I think I can fit it down here. So by L'Hopital's rule, what that tells me then is that my original problem, which is the limit as x approaches infinity, of 8x cubed minus 5 all over 4 minus 3x to the 4th, that is now equal to the limit as x approaches infinity of the derivative of the numerator. So the derivative of the numerator, we'll use the power rule. We'll get 24x squared over the derivative of the denominator will give me a negative 12x cubed. Well, this is one of those limits where if I do infinity over sub in it directly again, I'll still get infinity over infinity. So I could apply L'Hopital's rule again, or I notice that I can reduce this fraction down. So this would be equal to the limit as x approaches infinity of the x squared over the x will leave me with just an x in the denominator, since the third power is bigger and it's in the denominator. 24 over negative 12 will leave me with a negative 2. And if I do a direct sub in on that limit, I can see that I'd be getting 0 as well. Now again, I do think it's quicker to just compare your degrees here and use all those concepts that we had back from Unit 1. But if the problem stated to use L'Hopital's rule on it, you can definitely use L'Hopital's rule. We just have to do that additional step of reducing down before we directly sub in. So in this video, we learned about what L'Hopital's rule is. And to recap, L'Hopital's rule is another way to take limits when you have the indeterminate form of 0 over 0 or infinity over infinity. If I don't have those forms, then I cannot use L'Hopital's rule. So L'Hopital's rule does not work on every single limit problem. It only works when we have 0 over 0 or infinity over infinity when we try to directly substitute in at the beginning of the problem. Which is why our first step in using L'Hopital's rule is to separately compute the limit of the numerator and see what that would go to, and the limit of the denominator separately, like we did up here. Well, in example 7, where I have these green stars, but we did that in every example. We did it down here in example 8 as well, and up here in example 6 that we can see on the screen. So that is our first step when we're using L'Hopital's rule. That is showing that the conditions of L'Hopital's rule are met. And on AP free response, if you do not show this separately, or on a learning check or final for my class, if you don't first show that these limits go the limit of the numerator and the limit of the denominator separately, if you don't show each of those limits before applying L'Hopital's rule, you would not get any credit on a limit problem where you attempted to use L'Hopital's rule. We have to show that the conditions of the theorem are met. Once we've shown that, what L'Hopital's rule tells me is that my original limit is equal to the limit where I take the derivative of the top and the derivative of the bottom separately. I'm not using the quotient rule. I'm individually taking the derivative of the top and the derivative of the bottom separately. For the most part, that usually leaves us with something that we can directly substitute in and get our numeric answer from there. Some cases we might still have 0 over 0 or infinity over infinity. You can actually use L'Hopital's rule more than once, so I could apply it again if I needed to. I would just have to show that the conditions are met So I'd have to show the limit of the top and the limit of the bottom again for our new limit. But in this case, like on example 8, instead of doing L'Hopital's rule again, it'd actually be easier to just reduce down that fraction and then do a direct sub in from there. So that is what learning target 5A is about. It's a nice revisit to limits as we kind of recap and finish up this